Hello everyone, we're back again to continue what is left in chemistry. Today's lessons are going to be about the acid, the alkali, and the universal indicator. Okay, first of all, we're going to talk about acids. What do acids have in common? Like every single acid has a sour sort of burning sensation. A sour taste is like that sort of sting that you get when you just squeeze a lime on your tongue, or when you actually eat citrus fruit in general. Okay. The useful here acids that you might find around is like lemons, oranges, they both actually contain citric acid. Also vinegar, the one that we use in salads or in food in general, to give us that sour, stingy taste, which is used to pickle foods or to flavor chips. Containing ethanoic acid. Fizzy drinks as well, they contain carbonic acid, and tea contains tannic acid. So here it's a question, like, citric acid, where do I find it? I find it in such citric fruits like lemon, oranges, and vinegar as well can be used to pickle foods or to flavor chips, and it contains ethanoic acid. And fizzy drinks here, they contain carbonic acid, meanwhile tea contains tannic acid. Acids also have industrial uses, like sulfuric acid here is used in car batteries and making fertilizers. Meanwhile, nitric acid can also be used in making fertilizers and in paints. Okay, do acids actually have a dangerous effect on us? Considering the hazards, the concentrated acids, the one with high concentration, such as concentrated sulfuric acid, are extremely dangerous because these acids are corrosive. This means that the acid here can destroy the skin and attacks metals if it's spilled. The types of acid that are often used in science lessons are diluted. That means they are mixed with water to make it less dangerous. This means they have had added water to them. Diluted acid are not as dangerous as concentrated. They are not corrosive, and by then they're not irritant, so practically they won't irritate the skin. Your skin might become red and blistered if some acid was spilled on it. The acids found in drink and food, like lemons and vinegar, are extremely weak and diluted. That's why it's safe for us to drink them or eat them or use them. Whereas diluted hydrochloric acid is not. However, they may still sting even if they got into a cut. What do acids have in common? This was a question before in your tests. Okay, we all agreed that whenever I add vinegar, or I drink fizzy drinks, or I just squeeze a lime on my salad, or even just taste it, just dip it into sugar and lick it, I will still got that stingy, soury taste. So practically here, acids have in common the sour taste. Some acids are weak enough that we can even eat them or drink them, and some of them would actually burn your skin. But one thing that they have in common is that they contain the element of hydrogen, but the taste is actually sour. So here there's two different things I need you to concentrate. If I ask you what do they do, like what taste do they have in common, is actually a sour taste. But what do they have in common as a property? It's actually the element of hydrogen, like hydrochloric acid, HCl, sulfuric, H2SO4. So practically the hydrogen is a main element here. The next one is actually alkalis. The alkali is the opposite of acid because as we said that alkalis are dangerous, acids are dangerous, the concentrated ones, also the alkali. It will have that soapy, slippery appearance, but in the same time, they can also give you that sort of a slight burn or So many of cleaning products here that we use in our daily use, they contain an alkali like soap, shampoo, washing powder, and they actually have a soapy feeling or a soapy sensation. Some alkalis are harmful, however, many alkalis are harmless and very useful. Like for the bleach that we use, the oven cleaner, disinfectant, and washing powder, they all contain alkali. Toiletries like soap, shampoo, toothpaste also contain an alkali. Even some medicines like indigestion remedies contain alkali. So for an example here, when you actually bake a cake, you use baking powder to ensure that the cake is light and fluffy. Baking powder here contain an alkali called sodium hydrogen carbonate or sodium bicarbonate. Without it, your cake will be like biscuits. What do alkalis have in common? What do alkalis have in common? Previously, we said that acids have in common when it comes to properties the hydrogen. Meanwhile here, the alkali, they have the OH or the hydroxide group. So how do you differentiate the alkali from the acid? So the acid has hydrogen, meanwhile the alkali has hydroxide. The sodium hydroxide, for an example, is the alkali used in many cleaning products such as oven cleaners. Calcium hydroxide is used by gardeners when their soil is too acidic to make it a bit neutralized to make like plants grow properly. Many of alkalis in our homes are very dangerous. The most dangerous ones are the oven cleaners, the caustic soda. These substances are corrosive. They both contain alkali sodium hydroxide, which is so irritant. Other alkalis are classed as irritant rather than corrosive, like bleach and disinfect. The alkalis are often dangerous than acids given the same hazard classification. This is because it can be hard to rinse an alkali from the skin because it becomes so soapy. The indicators. Why do we use indicators and what are they? The indicators in generally, they are like substance or dyes that we use them. They have different colors. We use them. Okay, so here like the indicators, they are substance or dyes that have different colors. We use them actually to detect whether this matter, this substance is actually an acid or an alkali. For an example here, we've got natural ones and we've got the most common indicator around, like the most common of all. The most common here is called litmus solution, where it actually turns red in acid and blue in alkali, as you can see over here. So for an example, I've got a substance that I don't know whether it's an acid or an alkali, so I just add a drop of litmus inside of it, and I have the litmus paper. I could just like use it just to tell me like if it turns into red. Sometimes like I don't want to use like a dye, but more likely as a paper over here. So it's like two ways. I could use a droplet of this dye and put it like inside of this container. If the container or the solution inside of it turns into orangey reddish, that means it's an acid. If it goes purpley blue, it's an alkali. Or I could use it as like these papers. If it turns into red like here, it's like an acid. If it turns into blue, that means it's actually an alkali. Okay, so an indicator is a substance that has different colors in an acidic and an alkali. One example of the indicator is litmus. Litmus solution turns red in acid and blue in alkali. If a solution is neither an acid or an alkali, we call it neutral, like the water. The water here is actually neutral. The litmus paper is sometimes easier to use than litmus solution. Blue litmus paper turns red into acid if there's an acid, and red litmus paper turns into blue if it's an alkali. Most flower, fruit, plant and parts that are red, blue or purple can be used as an indicator. This is because these parts of plant contain chemicals called anthocyanins, that change the color in acid and alkalis. The real purpose of these chemicals is actually to preserve nutrients in the winter. However, we can use them as chemical indicator. Also, the red cabbage, you all know that kind of vegetable, the red cabbage. We can actually use it as an indicator as well because of its reddish color. The gardeners can use indicators to test soil. This is because some plants prefer acidic soils where others prefer alkali. Home swimming pools should be kept around the neutral. So the gardeners here use the indicators to test the soil because some plants actually prefer acidic soil, meanwhile others prefer the alkali, and also the home swimming pools should be kept around the neutral. Indicators can be used here to check the water has not become acidic or alkali. Industries can use indicators to check that the liquid waste that they dispose is not acidic or alkali. For an example, photographic industries use indicators this way. Now we come to the universal indicator. The universal indicator here, we use it to detect how severe or how or the much amount of the pH scale here. For an example, if I've got an acid, I just want to know, is it a strong acid or actually a weak acid? So here is the scale of the universal indicator. It shows me here that the strongest acid is always between 1 and 2. 3 and 4 are slightly weak, but as long as you follow here the arrow, it goes to strong and the opposite way around for the alkali. For an example, if I had a container telling me that the solution, the pH of the solution is actually 3, I would say yes, it's actually a strong acid, but not as strong as when it tells me that it's around 1 or 0. Okay, 7 here, it's actually most universal, it's around 6.5 and 7, so it's not always 7, the neutral. The weak alkali starts around 8, 9, 10, but starting from 11 till 14 it goes a strong alkali. So this is actually the purpose from the universal indicator, to make to give me a pH scale ranging from 1 to 14, and the 7 or the 6.5 is actually the neutral state. Okay, are all acids the same? We already said that no, it's not the same, because we've got concentrated, we've got diluted, we've got those who we can eat and drink without causing us any harm, and those that we can't even touch them because of their irritant property. If Oven Clearer got on your skin, it would burn. This is because it's a strong alkali. Soap also contains an alkali, but of course you can put it safely on your skin. This is because soap contains a weak alkali. Sulfuric acid is used when preparing skeletons because it can remove the flesh, the meat from bones. It's a strong acid. Ethonic acid is actually found in vinegar, so it's practically a weak acid. Most chemical indicators just tell us whether a substance is an acid or an alkali. Universal indicators turn a range of different colors. The color depends here on whether the substance is an acid or an alkali and how strong or weak it is. As we said previously, the neutral solutions here are pH around 7. The acidic solutions are less than 7, meanwhile the alkali are above 7. Comparing indicators, the litmus indicator turns red in acid and blue in alkali. Red cabbage indicator turns red in acid and purple in alkali. So the universal indicator is actually a mixture of several different indicators. This means that it gives me a full range of predictable colors depending on the strength of the pH or the substance. Exploring neutralization will stop here and will continue the next lesson.